Hello everyone. My name is Luca Pesce and I will present this work, Subspace Clustering in High Dimensions, Phase Transition and Statistical-to-Computational Gap. This is a joint work with Bruno Loureiro, Florent Zakala and Lenkas de Berova here at EPFL. I think that every one of us knows what is clustering, is a fundamental tool in every field of science, but we see from our title that we want to study subspace clustering. So what is it exactly? We have a subspace clustering problem whenever the relevant features of our data live in a lower dimensional subspace. For example, in this toy example, we have three-dimensional points, but the Z component is irrelevant. This is a very toy example. But this is subspace clustering is far from being a theoretical exercise. Indeed, it has been shown in very different data sets that the relevant features live in a low-dimensional subspace. For example, if we analyze the case of images, we can follow the work of Pope et al. In 2021. If we take ImageNet dataset, although the data has hundreds of thousands of features, the intrinsic dimension is estimated to be less than 50. So this, I hope, gives a quantitative idea of how important is the feature selection step in modern machine learning. So our goal is to build a model for subspace clustering that tests this desired property and study the statistical and computational limits for this task. Indeed, the main contribution is to say that subspace clustering can be, this is a little spoiler, can be algorithmically hard, and we will define what is it. And in the relevant regime, where the number of relevant features are low, we will see that there is an algorithmically hard region that emerges. What is the model that we use? We use a sparse k-Gaussian mixture model. Now, everyone is familiar with Gaussian mixture, but what do we mean by sparse? Sparse, we impose a sparsity constraint, which is to impose that all the centroids in our mixture have only S components non-zero out of the possible D. This is the sparsity constraint that creates the low-dimensional embedding that defines the subspace clustering problem. Another important conceptual step in our work is to map this problem to a low-rank matrix estimation one. Indeed, introducing three auxiliary matrices, V, U, and W, that encodes the information about the centroids, the information about the label, and the information about the noise, all the technical part I skip, but we can map the subspace clustering problem to a low-rank matrix estimation one. After doing this, we can answer the two main questions. When is statistically possible to infer the cluster label, and when is algorithmically possible to do so? We answer this by comparing the best-known algorithm for this task, which is a tailored approximate message passing, AMP in the following, with information theoretic performance. I compare the two, and I can define reconstruction phases, an impossible phase in which is statistically impossible to retrieve the subspace, an easy phase in which is easy algorithmically to retrieve the subspace, and a hard phase in which statistically is possible, but algorithmically not. We summarize this in what we call the phase diagram. And the interesting region is in the low row. I didn't define row, but you can understand that when row is small, the centroids have less relevant features. And looking back at what I said before, we go in the relevant regime, because the relevant regime is the large sparsity regime. So if we zoom in, we can see in this large sparsity regime, which again is the relevant one, we can see that what is defined the information theoretic threshold, so the SNR that we need to statistically solve the problem goes to zero. This makes sense in a sense because statistically the features that we have to keep track are less, and this goes to zero, so we have an impossible phase and a possible one. But unfortunately, AMP is not able to take advantage of this information, cannot use the row, as you see this algorithmic threshold in the large sparsity regime does not have row, and so there is an algorithmically hard barrier that opens up. For all the technical point, I see at the poster, and I thank you for the attention.